Okay, now we've seen that the wall test actually has some issues with power for beta going off to infinity. Can we come up with a test that does not have this problem? And the likelihood ratio test is actually a candidate for this. This is the second test you learned for hypothesis test when you do maximum likelihood estimation. And the likelihood ratio test is a little bit more general in the sense that we can try and test more general null hypotheses than what we're looking at right now, also for the wall test. How does it work? The idea is to not test how close the estimated beta is to something, but instead think about how much influence on the likelihood the restriction to the null hypothesis has. So if the null hypothesis is true, then restricting to it shouldn't change much, right? If the true beta j is beta j naught, then everything should be fine when you assume that it is exactly this in optimizing the likelihood. But if it's not, you get a little bit more wiggle room, and the likelihood ratio test is exactly trying to exploit this idea. OK, so likelihood ratio test. There you first calculate beta hat, as before, and then also a restricted estimator, beta hat c, which is going to be the maximizer of the likelihood again, so maximum likelihood estimator, but where beta now is restricted to the null hypothesis. So beta j is equal to beta j naught. And usually, when you have an algorithm that can optimize your likelihood, it should also be able to just fix some of the parameters, for example, to just beta j naught. So you can calculate this. And then what we do is we calculate the likelihood ratio test statistics. So it's a ratio of the likelihoods, which means it's going to be difference of the log likelihoods. And we multiply it by 2, which corresponds to squaring the likelihood ratio. And we plug in the maximizer into the likelihood, given our data, and we subtract off the likelihood for the restricted or the constrained estimator. Right, and then the theorem that we had, so you see that this thing should be larger because we are optimizing, we're maximizing with fewer restrictions. And the theorem was that this converges under a certain regularity condition in distribution, as n goes to infinity, to a chi-squared distribution with degrees of freedom equal to the degrees of freedom here minus the degrees of freedom there. So that's p minus 1, which is a chi-squared with 1 degree of freedom. So same cutoffs, and then I do my likelihood, my test. And my decision rule is going to be reject if the likelihood ratio is too large. That is, if it exceeds the alpha quantile of the chi-square distribution with 1 degree of freedom. The 1 minus alpha quantile. Yeah. OK, so that's one thing you can do. You'll notice that for this test, there is no normalization going on. So I just straight up take the difference of the likelihoods, which is also called a deviance or deviation of the likelihoods, and then I test how big is this. And again, asymptotic theory tells me this should also be a chi-square distribution, but maybe it doesn't have the problem that we observed before. Let's look at it. So first, this is what our test statistic for the wall test looked like. And now I do the same, but now I plot the deviance. And we see I plot the 2 times the deviance. And or the different two times the difference between the log likelihoods. And we see that indeed this looks much better. In fact, we see monotonicity except maybe at the very end. And yeah, that's it. So the likelihood ratio test does not have this problem. This also carries over and is a more general fact. So maybe if you're doing a logistic regression, this would be the test that you should be running. There are a couple of other choices that we're not covering here. All right, and with this we conclude our recitation about hypothesis tests for logistic regression.